Let me show you how to be a good Bayesian.
Today, I am excited to host Luc Bornn, a true pioneer in sports analytics and Bayesian statistics. Luc started his career as a statistics professor at Harvard and Simon Fraser before pivoting almost entirely to sports analytics over a decade ago. Luc has worked across multiple sports roles, including quantitative gambling, analytics leadership at AS Roma, and the Sacramento Kings, and co-founding, obviously, Zealous Analytics, which grew to a 75-plus person company before being acquired by Teamworks. He was also part of the ownership group at Toulouse FC, where he's applied data-driven decision-making to build a competitive club on a budget, winning both Ligue 2 and the Coupe de France. In this episode, Luc takes us through the evolution of player tracking data and the application of Bayesian methods in decision-making under uncertainty. We dive into portfolio optimization for player acquisition, the challenges of model validation, and the role of generative models in forecasting performance. Whether you're into sports analytics or just fascinated by decision-making in high-stakes environments, this episode is packed with insight from one of the best in the field. This is Learning Bayesian Statistics, episode 131, recorded December 10, 2024.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? Is someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is the place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. And if today's discussion sparked ideas for your business, well, our team at PIMC Labs can help bring them to life. Check us out at pimc-labs.com.
Luc Bornn, welcome to Learning Bayesian Statistics.
Yeah, thanks for having me on.
Yeah, thank you so much for taking the time. This is a blast to have you here. I never thought I would be able to interview you on the show. To be honest, you're kind of a superstar to me in my world, you know. So I'm very happy to have you here, and thank you so much to Patrick Ward for putting us in contact. Patrick, if you're listening, thank you so much. And when you come to Miami, I definitely owe you a good dinner.
Yeah, you know, anything Patrick asks, I do. So, and as prep for this, I went back and I looked at all your listened to a bunch of the previous episodes, and really cool to me to see your podcast in some sense resembles my career. Like the last, recent episodes, you have a lot of people that I call colleagues and friends now, Ravi and Patrick and Paul Sabin, and then I look farther back and it's like Julian Cornabis. Him and I worked together in North Carolina when he was doing his postdoctorals at UBC. We actually wrote a short paper together. Andy Gelman and I shared an office when I started at Harvard. Nicholas Chopin and I have had many dinners together over the years. Kevin Murphy, know well from my time at UBC. So it's really cool to kind of it really blends my sort of two phases of my career, sort of first as an academic and now sort of in sports.
Yeah, okay, that's good to know. Yeah, for sure. So I didn't know you knew Nicolas and Julien so well. I remember Andrew Gelman, which must have been really cool. Like honestly, working in the same hallway as Andrew, because each time I get to see him, it's really cool, and I get a lot of It's just awesome because he always has so many stories, and I can ask him any questions that I have. So working with him must be incredible.
Yeah, and we shared an office. My first semester at Harvard, I was actually on sabbatical, kind of a parental leave because I just had a kid, and I was going back and forth between Vancouver and Boston. Sort of we were in the process of moving, and so yeah, I shared an office with him. It was a really cool experience.
Yeah, I mean, I guess. And actually, something Patrick told me while preparing for the episode, he told me, so you can ask Luke anything about sports. He knows a lot about that and stats, but don't ask him anything about guitar playing because I'm way better than him, something like that. Do you know what he's referring?
Yeah. So I used to play guitar quite a lot. For those watching this on video, we'll see the guitars in the background. But Patrick is actually a properly trained musician. Actually, I have an interesting story about Patrick and guitar, which is, so I was at the Sloan Sports Analytics Conference. This is probably 5-6 years ago. And we were upstairs at Trillium Brewing, which is the sort of, nice restaurant, brew pub near the conference. And I was sitting at the corner of the bar, and on one side of me was Patrick, who works for the Seattle Seahawks. I think was on your podcast, a couple months ago or something. And Sonny Maida was on the other side of me, and he's an assistant general manager for the Florida Panthers. Incredibly interesting guy, just two incredible guys on both sides of me. And at some point, we were late into the evening, it occurred to me that these guys had just met, and they had this incredible unknown connection, which is Patrick actually studied jazz guitar at Berkeley in Boston, and so formally studied jazz guitar. Sonny Maida was actually a professional jazz guitarist in New Orleans for years, in addition to being a professional poker player and all sorts of other cool stuff. And so I said to these guys, I said, whoa, like you guys are both like leaders in sports analytics, but you have this really bizarre connection that neither of you realizes, and I do. And see how long it takes you to figure this out. So they started on academic stuff. It took them probably a good 20-30 minutes before they realized, and then I couldn't keep them apart for the next 4 hours as they just compared teachers and the musicians they'd played with and so on. So a long history, of course, of math and music being tightly tied together, but that was a cool example of two of my favorite people, and Sonny and Patrick sort of coming together on a musical interests.
Yeah. This is really cool. For those watching the video, this is the first time that happens. I'm in a new flat now, and I have a picture behind me. There is a face on that picture, and basically the iPhone is freaking out because it's seeing two faces, and so it doesn't know if it should focus on myself or the painting.
Going back and forth between the weird painting and you.
So I think I should take that personally, right? Because I look nothing like the painting, and the painting is pretty awful. So it's I'm taking it quite personally. I'm selling my iPhone after the episode. I'm gonna get rid of that painting actually while you talk, because it's way too distracting for people. So anyways, great story. I love that. And yeah, as you were saying, of course, deep history of music being actually very mathematical, and mathematics also being very creative and artistic in a way.
Absolutely.
We've talked about that already actually on the show.
Yeah, at Zealous, which we'll talk about in a bit, there's a very active music sort of culture. A lot of people who play instruments that are sort of hooked on music. Even one of them being Daniel Lee, who you've also had in the podcast.
Oh yeah. Mm-hmm.
Really cool guy, but just really super passionate about music as well. And I think it's a pretty common connection there for sure.
Yeah. So as you saw, I could not get rid of the painting. It's really into the wall. So we'll have to do that with that. That's gonna be a collector episode, folks. I encourage you to check the YouTube video of that one. I mean, Daniel is absolutely incredible. Each time I come to New York, and I get to meet him, he always gives me tons of recommendations, of stuff to do in New York. Very artistic. He's also very well versed into in architecture, which is something him and I have in common. And he knows really well architecture, and so that's really cool because he always gives me amazing things to go see in New York. So yeah, thank you so much, Daniel, for enlightening me all the time. Did you get a private concert when you were at the Sloan conference from Patrick and that other name I don't remember?
From Sonny, no. Patrick, though, in the past has sent me videos of himself playing guitar, and he's a much better guitarist than I am, so I have never reciprocated.
What's a talent of yours, actually, that, like something that, I mean, you're obviously talented in your job and everything you do related, but like a non-professional talent that you could send a video to Patrick?
Oh man, it's a good question.
Yeah, and I know I'm putting you on the spot here because it's not at all. It's the first time I asked these questions, and that was not in the questions I sent you.
I'm trying to think of sort of obscure talent. I'm these days, it's like my whole life is job and family. So I'm extremely good at losing to my kids at Mario Kart, and horrendously bad at putting together IKEA furniture. So maybe it's like good at being bad at child-related things.
So yeah, I mean, I don't know if you're already at the part where you're not losing anymore on purpose at Mario Kart against your kids, I
am at that point. My kids are a little older now. They're 8, 10, and 12, and so certainly the older two are, Super Smash Bros. I have no chance. I just mash buttons and hope I get lucky. So yeah, I'm well past that point. They're definitely better gamers than me.
Yeah. I mean, they probably don't listen to the show, so if you tell them you do it on purpose, I think you can still do it for a few years. Tell them, I did it on purpose. Don't worry. Yeah.
Exactly.
I made you win. Actually, yeah. So, can you tell us what you're doing nowadays? Because you do so many things, very original. So, yeah, what do you tell people when they're asking you what you're doing nowadays, and also how you ended up doing what you do and working on this?
Yeah, I tend to give people. It depends on how long of a conversation I want to have with someone. If I want to sort of end it quickly, that's what I do. I say I'm a statistician, and it usually ends the conversation right there. For longer conversations, I'm really fortunate that I have sort of a one-word description of what I do, which is Moneyball. Right. So certainly people outside of the field, what do you do? Yeah, I'm the Moneyball guy, and that's sort of a really easy way to sort of describe what I do. But yeah, if I give sort of a longer background, I did a PhD in stats and machine learning under Arnaud Doucet and Jim Zidek at UBC. Then I went on to spend some time on the tenure track at Harvard and then Simon Fraser. Through that time, sort of made a transition into sports, and we can talk about that transition later if you want, but sort of pivoted over to sports analytics, and since then have worked for a bunch of NBA teams, spent a few years with the Sacramento Kings, some consulting gigs with others. Spent a little over a year with AS Roma in Italy, a gig in quantitative gambling, and then the last sort of 4 or 5 years with some partners, we sort of banded together alongside some investors, and we bought Toulouse FC in the south of France, and another club more recently. And alongside that, I co-founded a company called Zealous Analytics, which we built up to about 75 employees, and we actually sold we sold Zealous to Teamworks back in the summer. So sort of just came full circle on that. So now my time is spent, I continue to work a little bit with Teamworks, with the sort of old Zealous crew, and continuing to be part of the operations of Toulouse.
Yeah. Okay, so Toulouse and not Milan.
Not terribly involved in Milan at the moment, that's right.
Yeah, because you still cannot be involved in both at the same time, right? Because of the European...
It's complicated.
Yeah.
It's complicated with UEFA,
Yeah. Okay. Yeah, that's just a great... such a great, path. And, we'll definitely dive into these latest activities that you were talking about, because I'm really interested in, how are the kind of models we're going to talk about, and we talk about on this show all the time, and I do personally in my everyday life, how are they used, how are they consumed by the people I make the models for, and that's something we have.
I get asked to do interviews and podcasts and stuff quite regularly, but it's almost always in sports, and I turn it down. This was like I get a chance to sort of like be nerdy again and talk about things that, the technical things that I'm super interested in. So,
okay,
fantastic.
cool. Oh, yeah, cool. So then, thank you so much. That's an honor. Yeah, and I think also if people are interested in a bit more about your background and stuff like that, I would refer to the I think it's the Wharton Moneyball podcast where you were a few months ago. I listened to that one to prepare for the show, so I'm not gonna ask you the same questions. This interview is really great because you go into detail, how you ended up doing what you did, your time at Sacramento, your time at Roma, and that's a great interview. So yeah, for people, I'll put that in the show notes for people who want to get a bit more detail about your background. Today, let's talk about Bayesian stats a bit. Like how
Awesome.
were you introduced to these weird world of Bayes?
When I got married and my brothers gave a speech, part of the speech was they said he's a proud Bayesian, and I can't remember. I just remember them like pronouncing the word Bayesian like really strangely. So it's clearly like part of my identity when it's part of a wedding speech. But I did my PhD at UBC, and at the time I was there, it was like this incredible hotbed of people in this domain. So did my PhD with Arnaud Doucet, and actually at the time there was like this really, it was him, Jim Zidek, who also did, another co-supervisor of mine, Rafael Guittardo, Paul Gustafson, Nando De Freitas, Kevin Murphy, and many others. So these people at the time, it's kind of all I knew, so I didn't kind of realize how special that situation was. But it was sort of, got to spend essentially 6 years of my life surrounded by those people, and kind of just deeply ingrained in me a sort of Bayesian way about thinking about the world.
Okay, yeah, so that was quite fast, basically, and that's kind of the way you learn statistics, if I understand correctly.
Yeah, I did an undergrad in mathematics, and then my master's and PhD were both in stats, and I sort of, my PhD thesis was sort of divided between sort of spatial stats and Monte Carlo methods, and so you sort of those two things together, when you think about sort of Bayesian spatial statistics combined with Monte Carlo, it sort of covered the whole gamut of sort of Bayesian modeling techniques. And of course, with Kevin Murphy there and Nando De Freitas, like also a lot of exposure to, what Kevin might call like probabilistic machine learning or statistical machine learning kind of thing.
Yeah, okay. Yeah, so that's funny because it's a bit like myself also, where I didn't have to unlearn, all the stuff I had learned very confusingly in undergrad. I like basically learned Bayesian stats from the start. Gotta make it simpler on the teacher, I would say. Like as a teacher now, right. It's way easier to teach people like us than to teach people who learned a lot of frequentist stats and now are trying to switch because naturally they always try to come back to something that's familiar, and sometimes it's very different. So you're like, okay, try to forget that paradigm. That's hard.
Yeah. UBC was interesting because you had sort of this Bayesian cohort, but then you also had people working on like robust estimators like M estimators and tau estimators, all these kind of very frequentist ideas. So it was kind of being exposed to both worlds. Like I think it was actually quite useful because it helps you really understand the sort of philosophical differences as well as the the pros and cons of different ways of thinking about things.
Yeah. Oh yeah, I think that's definitely super interesting and super worth it. And as I always say, for people interested in kind of the epistemological kind of side of things, the two best episodes to start with that we have are episode 50 and 51. 50 is with David Spiegelhalter, the only sir we had on the podcast for now. Maybe we'll get Alex Ferguson, one day. And 51 with Aubrey Clayton, the author of the book Bernoulli's Fallacy. If you want to start with some epistemological topics, I would definitely recommend these ones, folks. So yeah, just go on the website and look for those. But yeah, I think in my experience that I only give that to the students when they ask for it, because usually the way that works for people is they are mainly interested in in the practical side of things. And unless they are very nerdy like me, they're like, okay, but why is that actually interesting, and why is that working better in these cases, and interested in really the why, then I'll give that to them very happily, because I love that. But in my experience, and especially also for my bosses or else, I'm like, I just show the model and show why that's interesting and why that would help their decision making. And actually, you personally, so as we've seen, you've been involved in sports analytics for years. So I'm curious about so many things. But first, what's your vision on how the field has evolved, especially with the rise of different sources of data in different sports? And another question I have for you as a decision maker is, how do you approach modeling uncertainty in your decision making, whether that's with Toulouse or Milan less now, but like the different things and projects you're working on, and whether we're talking about evaluating players or planning strategies.
Yeah, so the first thing is about sports analytics. So when I started getting into sports analytics, at the time, it was the early days of player tracking data. So prior to that, all the vast majority of the data up to that point had been, event data, hand tracked, maybe a couple hundred or a couple thousand events per game, sort of true across sports. Baseball may be the exception there, but for most sports, it's sort of very simple data, count data, that kind of thing. And about 2012, I was really fortunate. One of the first people I met when I started at Harvard was a guy named Kurt Goldsberry. He had just been handed the NBA's player tracking data. And this data captures multiple times per second the location on the court of every player and the ball in 3 dimensions. And so to me, when I looked at this, I was like, this is, I'm actually not that big of a sports fan, but to me it was the richest space-time data I'd ever seen. And the amount of structure that exists in this data because of the sport itself, both the rules as well as the sort of tactics and strategy, it was just like the most fascinating and challenging problem I think I had ever come across. So for me, sports was not my path into sports was not, I want to work in sports, or sports is really cool. It's like, this is really interesting and hard and unsolved. And keep in mind, my PhD was essentially on modeling space-time, things in space-time, along with like SMC methods and so on, to handle these things in sort of computationally efficiently. And so I had the right toolkit to handle this type of data. So yeah, that was kind of how I made the transition from academia into sports, is fundamentally with these new data sets that are really complex and spatially and temporally rich, having the right skill set and just realizing actually, there's lots of interesting problems. For a while, I actually sort of consulted in sports and continued the academic gigs, and just found that I enjoyed the sports stuff more. The problems were more interesting. I never enjoyed going to committee meetings and reviewing papers and revising papers. That's the peer review process in academia is like fundamentally broken, and so it was an easy decision when I decided I'm going to go full time into sports. So anyway, that's the sort of sports piece, how I sort of pivoted to sports. The second part of the question, which is like handling uncertainty in decision making, I really think about that as the end user. We want to try and construct a team that's going to outperform its budget. So let me use Toulouse as an example. So Toulouse has a payroll of about 15, 18 million a year. That's euros, but our goal with that,
which is so to give perspective to people who don't know, sports, that's not a lot, right? If you compare
low.
To the big,
we are the lowest or second lowest in the league.
Yeah.
And our goal is to have,
and the biggest are like way bigger. Like they have way bigger payrolls than you do. The big clubs.
You might know a big club in France that has a insanely inflated payroll. There's a few of them.
It starts with a P and ends with SG.
And so, we're just to make the math easy. We're spending 15 a year. We want to perform like a mid-tier club, like a sort of an average club in the league, which is typically spending 40 or 50 million. So the way I think about us is like, okay, how do we spend 15 million a year? So that's like the lowest or second lowest budget, perform like the 10th or 11th best team, and that's sort of 40, 50 million. And to do that, we sort of have to have distributional sort of assumptions around the value that each individual player creates. And essentially it becomes like a portfolio optimization problem, where you have a set of players which sort of act like individual assets in a way, and you're trying to sort of find the combination of players that that you can have with some reasonable confidence that you're going to be able to perform to the level that you need. Certainly at the very least avoiding relegation, but sort of assembling these things in a way which you're trying to sort of decorrelate these assets, these player performances, and so on, and sort of such that you minimize your chance of relegation and maximize your chance of sort of performing at the level you want to perform at.
Yeah, and that's funny, because that's also a lot how I personally, try and explain the issue to, what I do to people, and why actually it's interesting for clubs to model with the kind of models we do, because often people don't know at all what's going on, in the front office. It's like, especially in Europe. In the US, I think, the influence of Moneyball, as you were saying, not only the book but also the movie, is much more pregnant. But in Europe, especially soccer, especially continental Europe, is like, really? People do that? So like trying to explain them in a way, as you were saying, as a portfolio management, where I'm saying, well, if you're, when you have less, remember when you were a student and you were broke, you had to be very careful about any dime that was leaving your account. So that's basically why also for the clubs which have way less budget, it's actually much more interesting to do this modeling, because they have to be much more careful about what they spend, whereas PSG or Real Madrid, like, it's not that big of a deal for them, at least at the beginning.
Yeah, certainly, a club like PSG, where you have such a high budget relative to the rest of the league, you can actually be fairly inefficient with it and still be quite successful, right?
I think they are. I think that's a good description of the club.
Yeah, and to boil it down to like a really simple example, let's say you want to acquire a player, you want to fill, say you're going for a striker, you have player A, player B. The traditional approach would say, okay, let's say player A costs $1 million a year, player B costs $2 million a year. And traditionally the scouts would say, well, we like player B better, so let's get him. But they say, hold on, one guy costs $2 million a year, the other one costs $1 million a year. One of them's older or younger, all these different factors. How do we choose one? And they have to sort of, either kind of comparing apples to oranges. They have these sort of financial traits, and then they have the scout saying, oh, I like this guy better. He's got a good left foot, and he has good spatial awareness. And you say, well, how do I turn that into dollars? Like, how do I decide whether I'm going to spend $2 million or $1 million on player B or player A? Whereas statistical methods come along, and you can sort of very precisely say, hey, there's a 10% chance that this player performs above his contract. There's a 30% chance that this other guy performs above his contract, right? So you can actually be much more explicit and probabilistic about the value a player brings. Most importantly, how they bring relative to their contract.
Yeah. And so, actually, how does that work for you? I'm curious, as the decision maker, as one of the decision makers, how do you actually use the models to make decisions? And I think for me, you would be one of the best bosses I could have, right? Because you come from the modeling side, so that would make my work, of course, way easier, because I could talk to you in technical terms, of course, but still, I'm very interested in how you personally consume the models. What is actually useful for you? Are those the posterior distribution? And is this something that you are more interested in the comparisons? You're more interested in the tail probabilities? What's actually something you care about when you make the decisions?
Yeah, I think the most useful way to think about for the end user is really sort of a distribution on future performance value. And what I mean by that is, you can imagine saying, hey, we think next year this player's performance on our team, and ideally in dollars, would be to say, some distribution over the value they will add in dollars. So if you look in basketball, it's like, maybe LeBron James is worth 40 million a year, but we might say, hey, we think that there's a 20% chance that he's, you think of some distribution, there's a 20% chance that he's worth 60 million or more, and there's a 10% chance because of injury or whatnot that he's actually worth 5 million or less. So understanding that distribution and then seeing how it progresses through time, that's the key information you need to make a decision about whether to, soccer, to sell the player or sign that player, or to extend their contract or renegotiate the contract. So that's sort of the key bits of information. And ultimately, we want to use that information as much as possible. I sort of think about a lot of what I do now is actually just removing humans from decision making. Sort of, there's so much work now in behavioral economics and elsewhere that humans are just quite biased in the way that they go about decision making fundamentally. And so, a lot of what I do is sort of focusing on, hey, how do we remove that bias from the decision making process? How do we take the good bits of sort of subjective information and remove those biases in a way which is ultimately going to create allow you to sort of create some arbitrage opportunity in player value, and ultimately to create shareholder value.
Okay, yeah, I see. So if I try to summarize, basically something like a WAR metric is how you summarize the contribution of the player, but that's still in terms of goals or wins or whatever, and then transforming that contribution to dollars and then making the decision based on that, and probably making a decision that's helped a lot by computer assistance to try and limit the biases that are very well documented in how humans make decisions.
Exactly. Like, one way to think about it on a player, if every single player on your team is underpaid, you are going to have a very good team.
Mm-hmm.
Right? Like, assuming you're paying, have a certain payroll, right?
Yeah.
Conversely, it's easier to think about the other way, right? If you have for a fixed payroll, if every single player on your team, if you have a low payroll and every player on your team is overpaid, you're going to be really very bad, right? So the goal is essentially to in getting as much performance value as you can for the dollars you spend, right? And history has shown that statistical models and sort of probabilistic reasoning are a much better way to go about that process than sort of the traditional gut feel scouting approach.
Yeah. But that's really fascinating to really see that research now pan out in real clubs like you're doing. So that's why I'm really fascinated by that kind of work. And also, I think these are great organizations as modelers, at least to work in, because that's also where your work has more impact, I would say.
Yeah, in sports too, you just get a tremendous amount of super interesting modeling problems, like sort of fitting the you talk about how to use Bayesian methods and so on, like how fitting the model is not the sort of interesting part, right? It's like even defining the model is not necessarily the interesting part. Where you get in, it's all sort of the issues that come around it that become super interesting. It's like if you've defined your estimand slightly incorrectly, you can end up with wildly wrong conclusions, right? Conclusions that can cost you millions of dollars. Or there can be there's probably lots of examples we can get into, but where this sort of standard model, think about what you're doing in sort of traditional validation of models. You say, okay, we fit this model, and then we sort of say, hey, this thing predicts well by some metric, RMSE or log loss or whatever it might be, right? We say, hey, this thing works well. And that's sort of a summary across all of the data. But think about what you're doing in practice when you're running a sports team. You're saying, I want the players who have really distinctly surplus value to add to my team. Ultimately, you're grabbing players from sort of the edges of the prediction space. If you think about the joint space of performance and dollars, the players you want are sort of at that threshold where they're cheap and they're good. right? And so if your you don't care about the bulk of predictions from the model. What you care about is the predictions in the space where you're actually actioning, right? So it's the predictions in the space of players that you're actually going to be able to action, whether it's players on your team or players you're acquiring, or of course that extends to ideas of strategy and so on as well, right? Sort of unique strategies and so on. So you care about pathological behavior and you really care about edge cases. So, and a lot of times in sort of in academic settings, it's like, hey, I fit this model, it works, it performs well, great. Here you're sort of saying like, I'm actually fine if the model in aggregate is slightly worse, if in the sort of space in the covariate space that we care about, or the prediction space we care about, it performs better, right? So there's lots of little issues like that come up in sports that are like super kind of interesting and make the modeling part of it, much more interesting. I'll give you another example, right? This is like so Bayesian but un-Bayesian, and see if we can sort of wrap our heads around this, which is there's this idea in sports called the Messi test, right? You've probably heard this phrase. Maybe it's like the Trout test in baseball or something, right? But the idea is that if you build a model for overall player skill, and this is like 5 years ago or whatever, but if you build a model for player skill, if Messi's not like at the top or close to at the top, your model probably sucks, right? It's like a very simple, like it's the eye test, right? Like if you build a model for best player, you want Messi to be at the top, and you can sort of imagine doing the same for individual skills, right? If I went basketball and I said if I built a model for the best 3-point shooter, if I didn't have like Steph Curry right near the top, like I should probably be concerned about my model, right? And that's actually like really insightful information. But if you think about what that is, it's typically not because, unless you're sort of like have some latent space of player skills, typically in this case, what you're actually doing is having some model that's like weighting different parameters and so on, and then you sort of like calculate it for each individual player to see where they land in this ranking. What you're actually doing is you're putting you have prior information about which players are good, okay? But when you're showing these rankings, essentially that's like the posterior predictive of the model, right? It's like the predictions from the posterior, so it's the posterior predictive, and you're saying I have information about what that posterior predictive should look like. So you're putting a prior on the posterior predictive, right? Which is like any like traditional Bayesian would say like that's just heresy, right? But it's like there's something there, right? And it's like actually valuable. So that's like there's all these sort of like super interesting things that come out in sports where you like have to think really deeply about the problem you're trying to solve and how your model sort of dovetails into that problem, and really sort of working on sort of those issues. I'll give you one more example here, and I could come up with more if we could keep going, where the modeling just becomes super fascinating. Which is one thing I've seen quite a bit is that there's a lot of these models that sort of capture overall player value, but they do it on the same units. So they say like, okay, in basketball, for example, it might be like points per 100 possessions. So like you could put a whole bunch of grad students and say, hey, you're all going to build a model for player performance on points per 100 possessions. And then they will do, like, they might have their analyst team go out and build these models, and then they say, okay, now we're going to weight these things to create an overall model, sort of like an ensembling or an averaging idea, right? And they might say, okay, but because these things are all on the same scale, let's make sure these weights sum to 1, right? Or a triangle prior on the simplex, right? But that's actually not necessarily the right thing to do, because each of these models in and of themselves has some shrinkage typically built into them.
Yeah.
And so it's very possible that on the whole, once averaged, there's actually more information in the sort of the aggregate model than there's in the individual. So there's no reason actually that you should do that. So if you don't kind of understand what's going into these models, why they're shrunken, why sort of multiple models combined might not want to be shrunken. And in fact, in this case, it's not even obvious to me that you should enforce positivity on the weights, right? So there's like all these things that I think if you go and just say like, hey, we're going to throw the obvious solution at some of these problems, you oftentimes end up with the wrong solution. So you need to sort of like deeply understand the models you're building, as well as the data you have, as well as sort of the underlying sport. And that's I think where it becomes super interesting.
Yeah. Indeed, that's fascinating. And what's really interesting to me is that, and that hints a bit about how useful these models and the Bayesian framework is in your work and at teamworks in particular. So I'm curious, like, if you can tell us a bit more about how you leverage these methods in your work at Teamworks or for Toulouse, and how you, like, and maybe to come back, to what you started doing in your career, how do they help account for uncertainty and thinking about the generative graph of the model with, in particular, spatio-temporal data?
Yeah, I think the word generative there that you said is really useful. That's kind of how I think about modeling problems, right? I very much think about, like, what is the generative model here, and how do we, in sort of, this may be a bit oversimplistic, but I sort of think about generative model as the way of specifying the model, and Bayes is kind of the way of giving the data, how you sort of work backwards, right?
Yeah.
Sort of the Bayesian, this sort of way of thinking, right, where you're sort of pooling information across, maybe across players or across matches or across seasons or across space, or this is all, like, incredibly important in sports, where you have what might look like a lot of data, but there's so much sort of contextual variation combined with a tremendous amount of players. So our database in soccer is about 80,000 players, and if you sort of, just think about, like, I want to fit even like an adjusted plus minus model, which is essentially like a giant regression model. It's a really, large P, small n type of problem. But of course, there's a tremendous amount of structure there, right? You have a lot of insights based on the league they play on, the positions they play on, how good, the team is, all as well as sort of individual event information that happens in the game. So you get, like, all this sort of super useful information and that comes from the structure of the game, and you want to be able to use that to get sort of better information, right? So when you talk about Bayesian models, that's sort of where it comes into play. Now, I should say that oftentimes what we end up doing in the end is sort of finding this balance between, hey, I want to, in my head, maybe I've specified this perfect model for this problem, but then either it's like it's too slow to fit because of the size of this data, is especially tracking data, can be absolutely massive.
Yeah.
So it's like, how do we get sort of poor man's Bayes, or like so oftentimes it's like, how can we get 90% of the value of this model for 5% of the computational cost, or 10% of the computational cost, right? So we get, there's a lot of those types of conversations go on. And then the other things that will happen is you'll sort of fit this model, and then you might, back to sort of the earlier conversation, you look at these edge cases and sort of the perimeters of the covariate space, and you're like, there's some bizarre behavior, and the model just doesn't look right in for various reasons in areas that we ultimately care about. And so then you sort of like have to think about, okay, how do we solve this, right? Do you like upweight that area of the covariate space in terms of the likelihood? Do you do sort of ad hoc corrections? Do you redefine the model, right? Like there's like all these sort of interesting things that are, I'll give you an example, one fairly recently, which is that we're building, you can imagine you have some model that says, okay, I'm gonna build component models for different skills, and then I'm going to sort of have those skills try and predict like player performance or team performance or something. So you can actually think of this as like multiple likelihoods in the same model, right? A likelihood for, there's some latent skills, think of them as like speed and ball control and whatever, right? And then you might be observing like actual speed data and maybe some of the team performance and a bunch of things, right? So all these different likelihoods sort of stack on top of those latent variables. And it turns out that because of this, whether it's like model misspecification or collinearity or something, you can end up in these situations where, the speed data in theory should define everything you need to know about speed, but because of the sort of incompleteness of the data or who knows what, you end up sort of, the likelihood for team performance, what can actually happen is to say, actually the speed data says this player's slow, but because he's so good, this latent variable for speed, we're actually going to think he's really fast. And so you end up in like situations where no, I don't want the player's performance or team performance to sort of flow into the speed latent variable, because subjectively, I think all the information should be captured from this other thing. And so you sort of end up doing things which are kind of on Bayesian, actually, which are like cut models, where you're saying, hey, I won't, like, even within, say, like a Gibbs sampler, right, where you're saying, I'm not going to allow this information to affect this variable or this parameter to sort of flow into this other parameter, right? So you're, based on the underlying model, you can sort of hack these models to do very, very interesting things. Actually, this is an old idea. If you remember, WinBugs used to have this like cut option, which sort of was largely for computational reasons, but allowed you to sort of like, in some sense, cut sort of portions of the graphical model to sort of produce what you want. There's actually some really interesting papers, I'll see if I can find it later, by Pierre Jacob that looks at these models, these cut models, and they're sort of like un-Bayesian in a way, but sort of shows how they behave and how they're super useful in certain cases.
Yeah, that is very interesting. It's like, yeah, I'm not sure it's un-Bayesian. Like, to me, it's just, specifying prior information and making sure it goes through the sampler. The issue you have usually, and that's actually an active area of research, is if the model gets complex enough, it gets hard to set the priors on something you really care about. Like setting the priors on the standard deviation terms of a multivariate normal is like, you have to do it, but sometimes it's not interpretable. What you have an idea about is the standard deviation of the whole data, right? So your whole generative graph, more or less the prior you want to have on the standard deviation, but you don't know how to specify that for each of the parameters. And so ideally you would want to specify one big standard deviation, and that one is just allocated then upstream to the rest of the model.
But this is even more weird though, because this is like saying we have some Gibbs sampler, so like maybe you're alternating through parameters, maybe it's these latent variables, right? And you're saying, okay, if we write the full joint posterior and then we break it down into the conditional so we can do Gibbs sampling, and we say, hey, this one, all the Gibbs samplers we're going to sample with whatever it is, maybe it's conjugate or maybe you can do rejection sampling, or what, it doesn't really matter. But this one conditional that we want to sample from, we're actually not going to sample from the true conditional as defined by the full posterior. We're actually going to sample from some version which looks like that, but we're actually going to cut out the dependency on this particular data source. So you're actually like, you're sort of creating this posterior, sort of artificially creating this posterior, which is actually not the full posterior you originally defined. You're sort of saying, you're defining some sort of new posterior, which is by removing certain dependencies within these conditional statements. Now, it's actually not necessarily true that you end up with like a valid joint posterior, but you end up with better performance. So it's just a super interesting problem to me, where, hey, I have this like, I know how things work on a broad scale for sort of the full Bayesian model, but I also know I can solve problems by sort of hacking these things and sort of pinning certain variables here and tweaking things here and sort of breaking things, but breaking them in a way which actually produces better results and ultimately better decisions.
Yeah, that's fascinating. I love that. So basically, it's like, if I understood correctly, when you say cutting the posterior, it's like making sure we're only taking a subset of the full posterior that the model was actually defining?
Kind of, yeah, but only on one of the conditionals, so only on one of the variables. So you're saying, hey, when we learn about the speed, so normally it's saying, hey, if I'm updating, let's say, the variable for a player's decision making, you have to condition on everything. It's the data, you give sample, you're also conditioning on the previous draws of all the other variables. But you're saying, then we're saying, okay, for speed, I actually only, when I update the speed latent variable, I only want to condition on the other variables, and the speed data, I don't want to condition on these other data. So you're sort of dropping the conditioning on these other variables and sort of just removing them from that conditional sampler. So kind of a really interesting case where you're sort of like just taking this thing that looks like a well-constructed posterior distribution and sort of just like hacking it in ways which is like kind of unprincipled but like makes sense and leads to the performance that you want.
Yeah. Damn, that's really cool. So I'm guessing that means a lot of custom code, whether that's in Stan or PyMC or PyTensor, stuff like that, right?
Yeah, certainly, right? It's a lot of these things aren't necessarily handled well with Stan, right? Because Stan is great for, or any of these models, PyMC, whatever. They're great for, hey, let's build like a Bayesian model that does this and this. But it's not great for when you're like, hey, we need to fix this edge case, we need to do this, and we need to sort of hack these things. So first up, to do those types of hacks, you have to like deeply understand the problem and deeply understand the models. That's sort of step one. But as you say, it oftentimes falls outside of these automatic inference engines. So you oftentimes have to do things custom, right? So, it actually reminds me a bit of like, I think a lot of times because of Stan and PyMC and others, like you oftentimes don't need to understand what's going on under the hood with HMC or any of these other algorithms, right? But I always thought it was important for people to understand, like at the very least, like what's going on when you're fitting sort of basic models. Like I'll give you one example here, which is when I taught spatial stats. It was a grad course. I would give people like a very simple multivariate normal where they're trying to like estimate the mean or the covariance or something, right? I'd say, okay, here's a whole bunch of data, and maybe p is 50 and n is 1,000. Hey, learn the mean and covariance, and that's like, oh, that's a trivial problem. It's conjugate, blah, 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 right? And then I say, okay, now I'm going to give them another data set, which is kind of the same thing, but p is now 1,000 and n is maybe 10,000. And all of a sudden, it's easy to pull in the data. The data is actually relatively small, but they go to fit the data and it just doesn't work. And they say, like, what's going on here? Why doesn't this work? It's a conjugate problem. Like, why doesn't it work? And they say, well, you're trying to invert a 1,000 by 1,000 covariate matrix, right? Like, maybe that's not a lot. Maybe it breaks down at 5,000. Whatever it is, it's a pretty relatively low number on sort of a typical laptop where these things start to fail. And then it's like, okay, well, that doesn't work. So go fit it with stochastic gradient descent. And then they go do that, and they say, oh, actually, that works way better for these large data samples sizes. And I said, but what about for the small data? And they say, well, actually, then just use the sort of the conjugate one, right? So it's like realizing that, hey, there's different ways to solve the same problem, and you might use this sort of direct sort of analytical solution in some cases, and you might prefer to use SGD in another. And then I go back and say, actually, there's a piece of information I didn't actually tell you. There's actually a certain correlation structure in this data, and it turns out to be just an AR1. It's a time series. Mm-hmm. Oh, now you can just fit this thing with like, Kalman filter-esque kind of, message passing kind of ideas, but you typically like Kalman filter. So you can do things in sort of linear time in P, because P is sort of T now, like time, what you think of it, right? So, and then there, and all of a sudden they go from an exact solution to something which actually is exact and very, very fast. So solving the same problem fundamentally, but understanding sort of there's different ways of actually doing the computation, right? And I think having those skills and sort of thinking holistically, not just about the modeling, but as well as the sort of fit, is really important. Like in sports where we're dealing with space all the time, you're sort of like, you're always having to discretize space in some way or another, right? Whether you like it or not, whether you sort of think about it as like, we're projecting onto some basis or something. Ultimately, you're discretizing. When you put it into the computer, it's discretizing it. So people oftentimes will say, "Oh, I like having a continuous model," but like, hold on, you're gonna have to sort of come up with some low basis approximation to it at some point. So might as well be sort of transparent that you're either having a sort of simple model that you can do like really accurate exact computation on, or a complicated model that you got to do approximate computation on, and sort of understanding those trade-offs, I think, is critical in anyone who's working on these problems.
Yeah, no, for sure. And that makes me think, in your experience, what have been the different ways, to get these 90% of the results with 5% of the computational cost of the models. What have you found particularly helpful? And I'm guessing these are cases where you cannot run classic nuts sampler, for instance, on a model. Right.
Yeah, a lot of this looks like it's like making sure you have a big enough toolbox so you can say, hey, here's the perfect way of doing this. Maybe it's like some big model built in Stan, but hey, that's not going to work as the data scales. So can we fit this with like a penalized regression? Or what happens if I sort of in a lot of these samplers, where things start to get really slow is when you're sort of sampling hierarchical parameters as well as sort of like in a lot of if you think about like a situation where you have like one variable per player, right? Those types of problems are oftentimes easy because you can marginalize them out. But as soon as you start sampling like hierarchical parameters as well, where you want like some some like group level variances or something like that, then those conditional updates can be super expensive to calculate, because then you're sort of conditioning on the full data, right? And so it's like, okay, what happens if we just like do some hack and just find an estimate for that hierarchical parameter, just plug it in, right? Do we lose a lot by just sort of specifying that directly rather than sampling it and having it posterior over it, right?
Yeah.
So that's like a lot of the types of things we're thinking about is like, where are the computational bottlenecks, especially as the data scales, and how can we make it work? Oftentimes work sort of in sequential updating, because essentially we want to update these things oftentimes like weekly as new matches come in. How can we do this sort of in a really efficient way without losing sort of prediction fidelity, right? And so it looks like things like, hey, actually this, if it's a big regression problem, can we do sort of penalized regression? And sure, we won't get full characterization of uncertainty, but can we get like a point estimate in 1% of the time? And then is there sort of ways, can we bootstrap or something else to get some notion of uncertainty around it? Or, as I said earlier, can we pin some hierarchical parameter to speed up the sampling, even though we know that, that's we're going to end up with some bias that results? So those are the types of conversations we're having constantly.
Okay. Yeah. That echoes a lot of the conversations I'm having also in my work, for sure. And so I'm curious, if you would be mentoring or teaching right now these students, what would you recommend them to invest their learning time on, provided conditional, and then knowing Bayesian stats and being fluent in a probabilistic programming language already, which is the case of a lot of the listeners here. But so if you had to tell them, well, something that can actually help you also complete your toolbox for these cases, for instance, what advice would you give them?
Yeah, one thing I've seen with like a lot of students that are coming out of master's programs or a data science program is that they're sort of quite good at give them a data set, say, hey, like either use this method or choose a method that's you're gonna get good prediction performance. And so, people are good at maybe tuning neural networks or Gaussian processes or penalized regression or what have you. They're sort of quite confident with these with sort of fitting methods and looking at predictions and saying, hey, this has a better RMSE. But where they can really sort of struggle is that a lot of times in sports, actually, there are certainly prediction cases, but oftentimes what we're doing is fundamentally is inference. You're saying, hey, we observe some team level performance where you want to infer what's causing this. So you have some latent parameters which are like player skills or player performances, and you're essentially trying to learn those. It's fundamentally an inference task. And so, thinking about more sort of statistical problems and sort of building that statistical toolbox, is the first thing I would say. Is if you're sort of the bulk of your time has been spent building prediction algorithms, is sort of broadening your toolbox beyond that, right? And then learning as much as you can. If you've some of the best ideas I've ever had in sports have come from like text modeling, right? Where it's like using like Dirichlet processes to model plays in basketball was like one of the coolest things I think projects I've ever been involved in. Again, that wasn't my idea. It was a genius PhD student named Andy Miller. But there's like those types of things, right? If you want to be able to sort of creatively solve these problems, to find computationally efficient solutions, you have to have way more than just one tool in your toolbox. So read broadly, study broadly, and get into the weeds on things, right? Learn about language models, learn about text models, learn about image modeling, learn about spatial statistics, learn about robust estimators, as we talked about earlier, learn about all these different areas, right? And sure, you won't necessarily be an expert in any of them, but if you sort of understand, hey, I know what these models do, and I sort of understand their pros and their cons and what they work on, what they don't work on, then it becomes much easier to sort of solve these these sort of unique problems that arise.
Yeah. That's really interesting to hear that. And how do you, in your experience, what have been very interesting open source software that maybe you've used outside of the Bayesian framework? I'm curious.
Yeah, early days for me was not open source. Like I started when I started my master's, it was like MATLAB programming, right? That's what I was like the tool du jour. And since then, I've sort of been a combination of R and Python has been the large bulk of my work. But a lot of stuff is built on packages designed for those two languages, as well as Stan and others, right? And in these days, a lot of what I do is also sort of broader technology, which is just like revolutionized the way we do things, whether it's cloud computing or Docker, like all these sort of standard tools in broader tech. I think are also, if you want to work in industry in particular, are incredibly valuable to learn, right? Like at Zealous, for example, like it's now Teamworks, we even have sort of our models themselves are like Dockerized, they're containerized. So you think about like, I'm building a Bayesian model. Well, we think of it as like a container object that holds predict functions and test functions and train functions and allows you to like very simply probe these models as well as to sort of version control them. And so it's like blending ideas from statistics and machine learning with sort of software engineering, ultimately to like solve a lot of interesting problems that come up in sort of productionalized machine learning, right? And so the truth is, it's a lot, right? But it's a lot also outside of what you might think of as like traditional stats and ML toolbox, right? But broader tech stuff. Heck, I spent a weekend. This is not work related, but I spent a weekend like flashing a Raspberry Pi and like messing around with a Raspberry Pi last weekend. So I'm like deep into this stuff.
Yeah. I mean, that makes sense to me in the sense that a substantial proportion of the modeling work is actually not done on the model. It's much like a lot before. How do I get the data? In which format? Which data do I want? Even before that, what's the generative graph we're thinking about? Which questions are we interested in answering? And then once I have the data, how do I format it in the format that the model can actually take it? Doing all the EDA, also extremely important. Parameter recovery, simulation-based calibration, all this stuff.
So this is something I hear a lot, right? Which is like, data science in the real world is like a lot more data munging and like all this sort of pre-model fitting stuff. That's certainly all true. I think the analysts that have worked with me in the past, where they're most surprised when they work with me is that how much work there is after that first model fit. So they do all this work getting everything in place, and then they're like, hey, I finally built the model, we're good to go. And I said, well, hold on. I want to see calibration. I want to see like all these different, I want to explore all the edge cases. I want to explore, what happened, how sensitive is it to different assumptions? How, is there like all these sort of like poking and prodding the model? It's like, so you have, there's all this work that comes before the model, and then there's sort of fitting the model, which is kind of the quote unquote fun part. And then before you sort of productionalize this thing and release it to the world, like you have to probe it endlessly to make sure that it does the things you want it to do, and that in sort of predictable and controllable ways. And that's sometimes more work than is actually needed before the models fit.
Oh yeah, I was gonna go there. Definitely. And I think that's almost always even more work, because that often doesn't work like you want to, the model,
exactly.
Especially if it's complex enough. So there's definitely some dimension where it's not working as you would have expected. And so that's interesting to know, okay, in which conditions do my model collapse, where does it not work? And so that takes, a lot of form. I think then there is, even after that, there is another part that is visualization. If you're doing that as the modeler, it's extremely important because you want custom visualizations depending on the people who are going to who you're gonna talk to.
Yeah.
We'll get to that a bit later, but yeah, on that model validation part, I think it's an extremely important part that you bring up, and that also goes back to something you were saying earlier, which is actually when we develop the model, we're fine if it's not doing a very good job at the league level, for instance.
Right.
But where it does a good job for the kind of players we're interested in. So it's like maybe the model is not that good overall, or it's not that good for all players because they have low athleticism, stuff like that, but we're actually interested in young players, so more bigger, like better athleticism and so on. In this population, the model is doing better, so it's actually fine for us. So that's the very important part. I'm curious, what's your workflow there if you have one? You know, if are there stuff that you always check once someone comes with a model that's fitting well, all the conversions and diagnostics are all good. Now we're entering that part of model validation.
Yeah, we do sort of a lot of stuff pre-modeling, you know, sort of project plan type stuff where there's sort of documents that we will use sort of to lay out the types of things we want to do beforehand. Afterwards as well, like calibration, so a lot of sort of standard things that we'll do. But a lot of it just is sort of fairly iterative, right? You do the initial sets of plots and then you say, actually, we should look at this and this, and then something looks weird and you say, okay, that's weird, like how else can we slice that a different way? Can we see it, try and expose what's actually going on under the hood? Hey, can we see this set of parameters? Is there some sort of like high leverage data that's maybe driving this weirdness? Like, let's explore all that type of stuff. So it's a combination of sort of a standard checklist, if you will, as well as sort of really custom stuff that really comes from just working with these models and these for so long that you sort of start when you sort of really spot little issues and you sort of figure out how to sort of pull the thread and to get at what you want.
Yeah. It's like a detective work. And what's like, is there a case, you know, that you remember that was particularly hard, you know, where you were like banging your head against the wall before finally understanding what was going on with the model?
Yeah, there's lots. That happens like this daily.
Yeah.
I'll give you one example. It ended up being my favorite paper I think that I've ever written. It was with Patrick. Very simple statistically. There's this idea in sports science of acute chronic ratios, and it's a pretty simple notion of, hey, how much load on your body has there been? I'm going to simplify a bit, so bear with me. But how much load has your body had in the last week versus how much has it had in the last month, roughly, or maybe month and a half? Just the idea being sort of like, hey, are you getting is the load that you've experienced recently, is this sort of normal to what you normally experience, or is it high or is it low, right? You can imagine if you're a runner and you sort of normally run 10 miles a week, and then this last week you ran 50 miles, well, you'd have a super high acute chronic ratio. And if you normally run 10 miles a week and this week you ran 1 mile, well, you'd have a really low acute chronic ratio. So it's sort of like a short-term average divided by a long-term average, right? It's the ratio of the two. And there's a tremendous amount of papers out there that show that if that acute chronic ratio is outside of some range, so here I'm talking about like load on the players, like amount of physical exertion. It's probably easiest to think of it as like running, right? It's like distance run, but it's a little more complicated than that. But they basically say, hey, if we have these notions of player load, and if you fall way outside of these bands, that it's highly predictive of injury in the future. Okay, and there's like some intuitive logic there, right, which says that. Which is like, hey, if I'm a runner and I go from running 10 miles a week to all of a sudden running 50 miles, I'm increasing my injury risk. I'm more likely to get injured moving forward, right? Or if I'm, training on the soccer pitch for 2 hours a week and now all of a sudden I'm going to 10 hours a week, I have a higher chance of injury. And to be clear, there's like literally hundreds of papers out there that show that is predictive of future injury. Okay, so great. So we have this acute chronic ratio. In fact, just as a little aside, the Apple Watch now, if you have the newest Apple Watch, has this built-in acute chronic ratios. It's like a plot that shows like how are you relative to the your normal. It's the same idea. and it's using a lot of these same ideas, but it's essentially like, again, the short-term average divided by long-term average. But when we did this internally, a couple of teams I've worked for, is that excuse me, we found that it wasn't predictive, and I couldn't figure out why. And so you look at all these papers, and basically what they're looking at is like their estimate is like a 0-1. Did the player get injured after some point in time or not? So it's like, if my acute chronic ratio is high at time t, do I get injured in time t+1 to time, let's say, in the next month or in the next week or whatever. That's how all these papers look. It's like the acute chronic ratio at a snapshot in time, because it's past, sort of looking backwards. Does it predict injury in the future? And then I realized, like, that's actually not what you care about, because what these are often saying is that, okay, if the main, what we sort of uncovered is that the main reason this is predictive is because if your load has increased in the last week, it also means that your load will likely be high in the future. And so what is actually happening is that your sort of like your chance of injury per minute of exposure or per mile run in the running example is actually oftentimes will stay constant, but your total underlying exposure has increased. So these are not actually this like great hundreds of papers that show this thing super predictive. It's actually predicting exposure more than it's predicting injury. And so so you end up with this like confounding with sort of, oftentimes it's like the time of the season, right? Like you come into training camp, your load spikes, and therefore you have higher chance of injury. It's not that your chance of injury for every minute you're on the field is higher. It's that you spend more minutes on the field after that, right? So like, I'll give you another example, right? If you looked at, eating ice cream is super predictive of drowning deaths. Like if you look at the data on this, you'd say like, okay, when people eat a lot of ice cream, there's a lot of drownings as well, right? And so it's like, what's the mechanism here? Are people like eating too much? People eat all this ice cream, they get bloated, they can't swim. It's like what your grandmother used to tell you, don't swim after eating. You sort of like make some causal stories that make sense of this. And then you step back and be like, no, there's actually a confounding variable here, which is like season. It's the summer. People eat more ice cream, they swim more, right? And so the ice cream is actually it's actually saying that it's predictor not of the drownings, but of the amount of water exposure. And it's the same thing here, that the acute chronic ratio is not necessarily predicting a higher, it's not like your chance of drowning per minute of being in the pool is any different. It's that your minutes in the pool goes way up. And here it's saying the same thing. So that's like a simple case of like, we did this big project, and it wasn't necessarily this new and novel, like, hey, we got this new thing. It was saying, hey, everyone's using this thing that turns out largely to be garbage, and it's or certainly at the very least they're putting way more confidence and trust in it than they should, because fundamentally all these papers have misdefined the estimand. They've defined it in a way which is actually not what you care about. You don't care about whether the player gets injured in the next 2 weeks. You care about their injury risk per minute of exposure, or per minute of gameplay or whatever, right? And you need to essentially control for that, and none of these papers have. So that's like a really simple example. Again, not terribly Bayesian, but sort of when you think really deeply about a problem, sometimes like this, there's like a really simple solution right in front of you that can, in that case, it's essentially telling people to stop doing this thing, or at least be much more thoughtful about how you're using this data. And so that's one example of like something that's still super prevalent in sports, but we kind of uncovered this really interesting confounding effect.
Yeah, it's fascinating. Yeah, and I mean, I love it because this really, like, you didn't find the solution in the data, right? So I think in a way that's quite Bayesian, because you had to, something that's fundamental in Bayes is solutions are not always in the data, and that's why you need priors, and that's why you need the structure of the model. And so here it's like literally thinking much more about the generative process of the data, and basically realizing, like in the ice cream and drowning example, where you have basically season is, as Richard McGareth says, is a fork, right? So because it causes both variable you're interested in, and unless you control or condition on that variable, you're going to have a biased estimate. And so here, thinking about that, then you condition on the time played, the time spent on the field, and then you see that this predictive aspect basically disappears because you've taken care of it.
In this paper, we also showed that if you use some ideas from, back to the point about having a broad toolbox, if you use some really basic tools from causal inference, like matching or propensity scores, that you can actually solve this problem, right? You can, if these studies, instead of saying, hey, let's predict whether a player gets injured or not, if instead you had said, let's take two players at the same point of the season, one who has a high IQ chronic and one who doesn't, but control for all the other things like minutes played in the games and all this other stuff, and if you did that, then you can actually control for this effect. And so, yeah, it's like, I think it's just a really simple example of a case like, have a lot of injuries are worth a lot of money to teams, and sort of understanding them well, and perhaps in this case, like not chasing, down rabbit holes.
Yeah, I love that. That's really fascinating, and that's a solution that's like simple, but it can take so long to get there. So, thanks. That's super interesting.
Yeah, that's not a big model. It's a good example because it's like there's no real stats there. It's just like a probabilistic. Yeah. I guess there is in a way, but it's like super simple. It's like it's a very simple case of this. Really, are you defining the estimate, the thing you care about, properly? Yeah. Because if you don't, you can end up with wildly wrong conclusions.
Yeah, for sure. I'm curious. So I'm gonna start winding us down now. It's like I've already taken quite a lot of your time. Maybe two other questions, if you can, before we go to the last two questions. I'm curious, what do you see as the most exciting trends or advancement now in your field, and how you think they will impact sports analytics and decision making?
Yeah, I think there's probably a couple things there. The first is, as I mentioned earlier, just the growth of this like really super interesting data and all the sort of statistical problems that come along with it. That has sort of been a trend over the last 5-10 years, but it certainly continues, and it means that teams and sort of other businesses in the sports space are investing a lot. So you have a lot of teams growing their analytics departments, and media companies and other sort of spending in this space. Another cool thing I've seen, which seems sort of like tangential, but is actually really, I think, actually quite nice, is that when teams are building out their internal resources, every team typically has to do a lot of the same things. So they have to like set up a database, they have to build all the ETL to ingest the data, they have to create like an IDM to sort of standardize across the different data sources, they have to map players. Anyone who's done like player mappings in soccer, where you have tens of thousands of players and you're trying to map, data from one data provider to another for some Brazilian player with like 6 names, like it's just impossible, right? And so everyone's doing these things sort of on repeat before you can get to like the interesting statistical problems, right? And so one thing actually that I think has been great, and it's a trend that has just recently started, and actually Zealous has been a big part of that, but there's others as well, is sort of realizing that's a problem and sort of like finding centralized solutions for that. So there's been cases, for example, of leagues taking some of that on and sort of saying, hey, all these teams don't need to each be spending hundreds of thousands of dollars a year like mapping players or doing this and this. We'll create something. Or Zealous has essentially said, hey, all these teams are doing a lot of the same things when it comes to data engineering and even sort of early, simple stage statistical modeling. Like let's sort of democratize that, and for a fraction of the cost, teams can just sort of ingest all that, and then they sort of start to use a baseball analogy. Like they're not starting from nothing; they're kind of starting on third base, right? So that's sort of another thing that I think is like a huge progress in terms of creating the space for sports analysts to actually work on challenging and interesting problems.
No, for sure. I mean, so first, now that I work in baseball, I can understand that metaphor. So thank you. and second, I mean, I'm an open source developer, so I'm not gonna tell you this is a wrong direction. I think, ideally, if you'd ask me, I'd be like, I think the leagues should just take over all of that and put all that tracking data and stuff like that. Not the latest frontier, because the industry to keep progressing, people still have to earn money because they were like the first one to develop that kind of data. But the old data and stuff like older data and stuff like that, just put that on the league, and then the league could just open source everything so that everything gets access to that, everything has the same data, and then it's just how you use the data and the combination, not only of the models, but the combination of the people working on the data, the modelers, the GMs, the coaches, like all these people together, the scientists. That's what really makes the value out of the team, much more than having that exact row in their database that the other team doesn't have. I think the rest of the other industries also show that,
Yeah, our edge at Toulouse did not come necessarily from having the best data. Like, I think we did actually have the best data and the best models, but it came from execution. There's no question about it, right?
Mm-hmm.
Like, yeah, we probably did a little better than if we'd had simpler data from the models. Yeah, maybe we would have been a little less efficient. But there's a lot of clubs out there, and I certainly won't say names here, but a lot of teams out there that have great data and big analytics groups and so on, and they treat them like houseplants. They stick them in the corner and ignore them, right? And you're not going to get any. You're not going to create competitive advantage doing that.
No, for sure. I mean, I see that a bit like high quality cooking. Right, what makes a chef good is not only the ingredients. It's like how they use the ingredients and with whom they are using that and to whom they are feeding the plates and where they are feeding people. If you go to big restaurants, it's like it's not only one table where they just give you the food. It's like a whole experience. So I think it's a great thing that we're moving in this direction, and yeah, as you were seeing, Zealous is doing a lot of that, and I think that's really amazing. Another question I have for you before the last two ones is, what's next for you? Because you're a very curious person, and now you've sold Zealous. So I'm curious, are there any upcoming projects you're particularly excited about for the month to come?
You know what? I sort of spent the first 15 years of my career sort of trying to be the best statistician as I could. I sort of had this personal mantra. I was always personally offended if I didn't understand something, or I didn't know a method, or I didn't, that was kind of that's part of what drove me, I think, to learn so much. Is just feeling like I just wanted to sort of cover everything. And so I spent so much of my career doing being that, right? And sort of growing as a statistician, and mostly in academia, but of course with various consulting gigs and elsewhere sort of in industry as well. And then the last 15 years have really been about, and some overlap there, but the last 15 years have been about sort of sports and learning about sort of applying that domain really into sports, and sort of how that leads to sort of decision making, negotiations, sort of finances, and the whole the integration of all those things coming together to ultimately go from, hey, how do we value players better, right through to running a team and ultimately outperforming our payroll, and all the way through to creating equity value for shareholders, right? And I kind of feel I'm at this point where I've built a lot of time, maybe it's hit Malcolm Gladwell's 10,000 hours in both of these things, and I feel I'm with Toulouse we've sort of proven the thesis here, and so a lot of right now what's next for me, I sort of want to keep leaning in on this. I feel I have these two things sort of perfectly hybridized together, where these technical skills that I've built over the years combined with the team management skills, and it's a super powerful combination and a really valuable combination. And so I just love using those tools and these ideas to sort of play Revenge of the Nerds in real life, right? Going out there and just dominating, using essentially, this is going to sound very not humble, but using our group's intellectual advantage to win, right? And to me, that's super, super fun.
Yeah. I mean, love that. Definitely support it. Revenge of the Nerd, you had me there, But yeah, I mean, of course, yeah. And that's something also try to do with the podcast front, trying to percolate these ideas through more people, because I think that's something that's needed a lot. So yeah, awesome. Well, Luke, I think we'll call it a show. I would still have so many questions. Like literally, I still have so many questions I had for you today. I didn't ask you.
Sorry, that's my fault. I filibustered a couple of those questions there. So
no. That's me. That's also my job. I have to adapt to the topics. But yeah, I mean that's cool. That means you can come back on the show next time you have a cool project to talk about, and I'll get you a few of these questions.
Great.
But first, before you leave, of course, I have to ask you the last two questions. Ask every guest at the end of the show. So I'm gonna change a bit the first one for you. First time I do that, but I think that you kind of answered a bit the first one already, and I'm curious because you have a particular background and origin story where, if I remember correctly, in its Moneyball episode, you were saying that you actually started working on spatial temporal data with the Sacramento Kings because someone came into your office with like some question, but the question was actually not for you, I think, if I remember correctly. And that's a very, very random, origin story where that could be in a movie in a way, right? It's like the hero never wants to be a hero, right? It's like the situation imposes onto him. So my question is counterfactual for you. If that moment had not happened, right? If you had not been in your office at that time, at that place, and you hadn't met that person and ended up working on sports data, what do you think you would have done?
Yeah, I think everyone's lives are sort of built up with a lot of these just kind of random events that accumulate into who you are. That was certainly one of them. I won't retell that story because, as you say, it's on the Wharton Moneyball podcast. But I think I'd still be working in sort of very similar space, but possibly not sports, right? Sort of taking all these ideas, Bayes and so on, and trying to apply it to some interesting problem. Now I, for some reason, ended up working in a space which is, working on a zero-sum game where billionaire owners are trying to extract value from millionaire players, and the millionaire players are trying to get dollars from the billionaire. So it's like a very strange space to work in, but I think I'd probably be in a very similar spot, but not in sports. Whether it's I was on a path where I was doing a lot of stuff in climate, maybe it'd be that, maybe it'd be sort of some other domain, but I think it'd be sort of the same thing I'm doing now, but just a different domain other than sports.
Yeah. I was thinking maybe agriculture. They do a lot of spatial temporal stuff over there.
I actually published a paper once on crop yield predictions in the Canadian prairies. How exciting is that?
Yeah, exactly. That's actually, we worked on a similar project when I was at PIMC Labs, and it was exactly something like that. Yeah, Gaussian processes. So that's a cool space because you can use a lot of Gaussian processes.
Definitely.
That's also very challenging because Gaussian processes are hard to fit, but they are such cool beasts. And second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
Yeah, this is interesting because I know you've asked the same question to others, so I've sort of gave it some thought. And I've been really fortunate that over the last 20 years or so, I've had a lot of tremendous dinners with people, right? Whether that's in academia, like I just have great memories of dinners with people that you probably know, Christian Robert and So I had this amazing dinner in Bristol with Julian Basseg in the last year of his life. He was a visitor there in Bristol. Peter Green at the same time. Just so many incredible dinners and then of course now in the sports world with coaches and owners and so on. I've just been really fortunate. So in sort of like the explore exploit, I think I have a pretty good idea of what like the distribution of good and bad dinners are, and so I think there's a really good chance that if I named a name of someone I'd never met, that it would be sort of below my expected return if I were to sort of exploit if I were to explore rather than exploit. So I think I would have to say to sort of look at some of the people that I've had some of the most interesting dinners with, and I thought about this a little bit, and I think the person I would name is Zhao Meng. So Jelly was the chair when I was hired at Harvard, and then later became the dean. And he is perhaps one of the most fascinating people I've ever met. He's just full of wit and humor and intelligence, and just a kind human being. It doesn't hurt that he has a giant box of scotch sitting under his desk, which can come in handy at times. And so, yeah, I think I would not explore. I think I would exploit. And by that I mean I haven't had dinner with Zhao Li in probably a decade, and I would love to sit down with him again.
Nice. Yeah. Well, I really like the structured answer. I think I never had that yet. So thank you so much. Yeah. Awesome. Well, I think that's let's call it a show. Luke, that was really amazing. I'm really happy because we get to explore a lot of the questions I had for you from a decision-making perspective, but also got to be very nerdy. So that's great. Thank you so much. As usual, we'll put links in the show notes for those who want to dig deeper. Thanks again, Luke, for taking the time and being on this show.
Thank you, Alex. It was a blast.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbasedstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbasedstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbasedstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.